Good morning. Let us resume our discussion. So what were we discussing in the last class?
We were discussing how to take the derivative when the expression have both vectors and matrices.
Right.
When the expression has both matrix elements. So
Right.
we came to the conclusion of a tensor and the representation of tensor in form of delta function.
Right.
Then we went for writing cost functions in different ways, that is in terms of probability and scores. So then we discussed about binary classification and multi-class classification, how we can represent those matrices. Then we talked about posterior probability or predicted and the true probability. And then we concluded our discussion based on how we can compare these two probabilities. And we talked a bit about KL-divergence and entropy.
Very good. So let's resume the discussion that we had at the end. So usually it is preferable to represent the classifier outputs in terms of probabilities. The reason being we can easily understand them in terms of how close we are to the true decision or true probabilities. Okay, so it's in many cases what happens is not necessarily even if you have 10 class classification problem, the input sample mostly belongs to one of the class. So there is also a feasibility of using the true probabilities as one for only one class, the true class, and 0 for other classes. Okay, so even in such case or otherwise, it is more convenient to have the output of the classifier in terms of probabilities and comparing with the true probabilities. Okay, so before we get into the discussion on the mathematical expressions for KL-Divergence, how do we compare exactly true probabilities? So let's start with say if we have any probability density function, how do we quantify the information content in a probability density function? Assume that some PDF is given to us. Okay, so something like 0.2. Okay, let's take a simple case 0.2, 0.8. Okay, where you have actually two outputs that are possible, and the sum of these outputs is 1, that is representing the probability density function of the two outcomes. Okay, so now in such case, so if I just want to know the information content in it, this is one possibility. The other possibility is 0.5, 0.5. Okay, the other possibility can be just simply 1, 0. Okay, and then 0, 1. Okay, different possibilities, but for the two outcomes that make up. Okay, in that event. So now in these different scenarios, if I want to measure the information content, how do we measure? Any idea on this? So this you can consider as P1. Okay, or Q1, Q2. Okay, they are probabilities of class outcome 1 and outcome 2. Okay, so in such case, how do we measure the information content in this probability density function? Any idea on that? Okay, it is measured through entropy. Those who might have taken any in like information theory course or any communication course also would have introduced to it. In fact, even the probability and random variables also may have this term introduced. So what does entropy does is it quantifies the information, or more clearly, it quantifies the uncertainty. Okay, so is the uncertainty high or low? It tells. It uncertainty is inversely proportional to information, or uncertainty is directly proportional to information. So in uncertainty is high means there is a more information that is necessary. Okay, or in that it is more information you need to extract. Okay, so yeah, how do we define entropy? Is okay. So if we have actually this Qi as we discussed, Qi ln of Qi. I equal to 1 to 2, where since there are two outcomes here. Okay, this is how the entropy is defined. So if we just compute for any of these, say for a trivial case, if you compute, what's the entropy for when you have actually 1, 0 as the outcomes? What is the entropy in that case? What is the entropy? Say the entropy, when we want to calculate, what do? We simply expand this. Okay. So that is Q1 ln of Q1 plus Q2 ln of Q2. There can be two outcomes or even multiple outcomes. That's why I have written with I. Okay. So I can go from 1 to 2 if there are only two outcomes. If there are multiple outcomes, 6 outcomes, I can go from 1 to 6 and so on. If it is a 10 variable output variables, it can go from 1 to 10. Okay, so now what's the say entropy? So this is represented with H of Q here. Okay, so you can, since this is a vector, we can also use a bar or bottom bar or upper bar. Okay, to represent vectors. Okay, so now what is this entropy in this PDF? So can one of you tell when Q is equal to 1, 0? What is H of Q?
0.
It is 0 because, okay, this first term is 0. Log 1 will become 0. Okay, 1 into log 1. Second term is 0 into. Okay, that is also 0. So whereas if Q is given as, okay, sometimes usually people also give capital Q. Okay, so it's based on our notation. Since it's a vector, I have written in small but with a bar, okay, upper or lower. Usually what happens is for the matrices, we will use capital letters. For vectors, we will use small letters only. With say usually bold is what is preferred in textbooks. We will write with upper or lower bar. Okay, that's the convention we can follow from now on to make our understanding easy. Okay, so now if it is 0.5 and 0.5, then what do you think it will be? Usually what we take is this, we take with log 2 instead of ln. Okay, of course it can be defined with ln as well, but it's defined with log 2 for the advantage that we can directly quantify in terms of the number of bits that are necessary to encode this information. That means if the PDF is 1, 0, okay, you don't need any number of bits because you are certain that all the time, okay, the probability of first event is 1 and second event is 0. Okay, you know that anyway that event will happen. Okay, so no need to send any information. This probabilities itself will clarify whether the event happens or not. Okay, but if it is the probability of first event and our first outcome is possibility of first outcome is 0.5, second outcome is 0.5. Okay, in such scenarios, you are not very clear which may happen, and hence you need to communicate the bit at every instant. That means in a if we are communicating a information, okay, so when we conduct several experiments, each time an outcome will come. That outcomes, if you would like to know at the other end of communication, okay, so we need to give the in terms of bits whether it is outcome 1 or outcome 0. Okay, if we assign outcome 1 to 1 and outcome 2 to 0, you have to keep sending 1 or 2 which comes as the outcome. Okay, and the average number of bits to convey an information is referred to as that can also be quantified by entropy. In fact, the minimum average number of bits that are necessary to convey an information are quantified by entropy. Okay, so now in this case, what is H of Q bar? Can some of you, if we just go by say half, ln, as I mentioned, base 2 is what used when we want to quantify in terms of bits. Okay, otherwise simple ln can also be used. Let's use base 2 just for our simplicity of calculations. Okay, half ln 2 half. What is the answer? Can one of you tell now? What is its answer now?
1.
Yeah. Okay, so it's 1 bit is necessary. Okay, on an average to communicate. Okay, a particular information. So 1 or 0, that's what the bit. See, if we see the entropy, with say one of them, say if we write just Q1 or Q2, assume that it is in Q1 is 0, then assume that Q2 is nothing but 1 minus Q1, just to make our job easier. Okay, and then with respect to Q1, we would like to have a information content plotted, okay, or the entropy plotted. So when do you think you need actually when the entropy is highest? Q1 can take from 0 to 1, right? As you know, so it is 0.2, okay, 0.4, 0.5, and so on. Okay, 0.6, 0.8, and so on. Okay, when do you think the information content, okay, in Q is the highest for these values of Q1? Any guess on this? Okay, Q bar, you want to check one more thing. So 1 by 4, so assume that 1 by 4, this is, okay, 3 by 4. Okay, just to have another example. Okay, in that case, what is H of Q? So some of you can quickly calculate, but until this will be lesser than 1. Okay, you can see that. You can anyway calculate and complete here, but it will be lesser than 1. So what will be the, when the, say, uncertainty is maximum, you can easily understand in terms of the uncertainty, or the information is high when the uncertainty is high. As I mentioned, that means the aspect to know is high. Okay, that's the information. Okay, so now what's the, when the uncertainty is high, or when to quantify when the entropy is high?
When both are 0.5,
So it will be like this. It will reach peak when both are 0.5, and then it will keep peak. Okay, so this is roughly the entropy versus the a particular probability of a particular event. Okay, so it will be highest when it is 0.5. So this is a measure of information in some sense. Okay, why we are discussing about the measure of information? Because when we want to compare the output predicted probabilities, we want to see how much information, okay, in this is lacking when compared to the true density. Okay, so if I say that the true density for a particular sample is this, okay, where it is 0, 1, 0, 0, 0, and so on. That means the sample belongs to second class. That is the true probability density function. Okay, but the predicted probability density function may be Q1 to Qn. So how far are we from P? Okay, is what need to be quantified in terms of a cost function. So first we should have a measure of information. That's what we have discussed so far. This is a measure of information.
Hello, sir.
Yeah.
Sir, can you again define what exactly information here means?
Okay. See, assume that we just tossed a coin, okay, and then we will get either head or tail. Okay, if we get head, we want to send 1, and if we get tail, we want to send 0. Okay, and the coin now is unbiased. First, it is a biased coin. Okay, and that's the first example. It's a biased coin with head probability of head equal to 1. Okay, so it's biased coin. In that case, see, I know the probabilities. Initially itself, I know the probability of head and probability of tail. Okay, that's a known before even experiment. Okay, in such case, do I need to communicate? Say I may conduct the experiment for 10 times. Okay, so should I need to send every time 1, 1, 1, 1, 1 to the other end to communicate the outcomes? Yes or no?
Yes, sir.
So should I need to?
We don't have to communicate because we already know it's already going to be biased.
Right. Right. So that's way the uncertainty there is 0. Okay. Similar to uncertainty, what also we have is information is also 0. Or if you consider that it is fully known, okay, so the information is known. If you consider information as the like the inverse of uncertainty, information is known. But if we are quantifying the amount of information to be known, okay, that is 0. Okay. So uncertainty here measures the information to be known. Okay, further. That is 0. So that in this example, it is 0. Right? Now take the example 2, wherein actually probability of head equal to 0.5. Okay, it's an unbiased coin. And now what will happen? And then anyway, you know that probability of tail is also 0.5. And then I keep getting 1, 0, 1, 1, 0, 0, 0, 1, and so on. Okay, I need to communicate the information again. In this case, how do I know how much information, how much is the uncertainty associated with this this experiment, or the information to be known? How do I quantify? Okay, that's how is exactly, that is what exactly is being done by entropy, through entropy. Entropy quantifies the uncertainty given the probabilities. So even in this case, assume that the probabilities of head and tail are given. If I give information of head and tail, do you think that we are sure that what the bit we get? Are we clear on that?
So say
Yes.
0 is the best case. Entropy 0 is the best case. Means we know the outcome.
Yeah. See what you are saying. This is the best case where we know the outcome. This is the case where we don't know the outcome. Is that what you are saying?
Sir.
Yes, that is true. That's true. I am asking in the second example. So if we convey now the probabilities, are we sure what bit do we get at the other, like what outcome do we get? Are we sure about it? Yes or no?
No, sir.
No, right? So that means there is some information, okay, in each of the output that we are getting, or there is an uncertainty in the outputs that we will be getting. Is it not? That is being quantified by this entropy. Okay, so entropy quantifies. It is easy to define like entropy as the measure of uncertainty, because it directly quantifies how much uncertainty is there associated with these properties. Okay, and it can be considered as, in that outcome, if you see the information, it is an inverse measure of information. Okay, more the uncertainty, lesser is the information there. Okay, that's what is the understanding. Is this clear now?
Yes, sir, it's clear.
Yeah, fine. So this is required, because if you would like to see how much we can't compare PDFs like the usual vectors through Euclidean distance, because of course you can also compare through Euclidean distance, but a measure which takes the information into account in comparison makes a more sense. Okay, that's why we are defining or discussing about these things. So P and Q, if we consider Q as the predicted probability and P as the desired probability, we can simply compute the Euclidean distance to see how far one from other. Euclidean distance, what it does in Cartesian space, how the two vectors, say whatever maybe in 2 dimensions or 10 dimensions, okay, how the vectors are far away. Okay, how much the vectors are far away. That is being seen by Euclidean distance. Hope you got this point. So when we see Euclidean distance, what we are seeing is, if it is in 2 dimension, okay, if we have 2 vectors, so we can just simply say this is one vector and this is another vector, okay, and this is some other vector. What Euclidean distance tell? In this say Euclidean space, in this is a 2 dimension, yeah, how far these 2 vectors are? What is the distance between these 2 vectors, and what is the distance between these 2 vectors? Okay, that's what is being conveyed by Euclidean distance. Okay, but this may not be a very good measure when we have the probabilities or PDFs, because the range itself is confined to 0 to 1, and they have a nice interpretation of giving the information of each of the class probabilities. Okay, how much a class, like the input sample belongs to a particular class, that information is there in that PDF. So using a measure something related to information makes more sense. That's why we are defining this. Okay, or discussing this. This entropy gives an inverse measure of information, okay, or a measure of uncertainty. Okay, hope this is clear. This is fine, but when we have 2 probabilities, say assume that P is the desired probability and Q is the predicted probability. So in that case, what we wish to do is, we want to see how much is the commonness of this information. Okay, this is desired probability. And this is the predicted probability. So what we should see is now assume that if this is known, okay, predicted probability is known, how much more information to be known or uncertainty is there to have information content in P. Okay, so this is what we need. Also, I assume that, see, if we don't have any information, then we start finding out the desired probability. Then what the measure of this desired information? Okay, directly the measure of desired probability in this is, desired information in this is, okay. So H of P or the entropy of P will give us what is the uncertainty. Okay, in this like the PDF represented by P, or the desired information, measure of desired information in P. Okay, but if we know already predicted probability, how much more should we know to get the information? That can be defined through KL-Divergence. While defining the KL-Divergence, there is one more term that is usually is necessary. That's necessary is the cross-entropy. What cross-entropy is defined as? Okay, again, I'm going back to capitals. Okay, so cross-entropy is nothing but the information content. What is the commonness of information? You can consider this as okay. So KL-Divergence, if we define, this is how usually is written. I will define it first. This is how KL-Divergence is defined. So what this measures? You can see in the expression, I'm writing minus of minus, just to have the measure in terms of entropy. Okay, so what is this? The second thing is HPQ. Okay, minus HP, because there is a negative sign missing here, right? So this is what is KL-Divergence. What this gives is, what does this give? So if we know already Q, how much more we should have to have the full knowledge of P? Okay, that how much more information to be known or uncertainty is there to have information in P when we know Q. Okay, that is being given by this. So this is in some sense can be considered as a dissimilarity measure or a distance measure. between what? PDFs, P and Q. Okay, and cross entropy is a like information, commonness of information, as we discussed. Okay, so now let us see some examples on how we compute this. So we have some examples where we have actually mathematically computed the KL divergence as well. So I have taken from a reference some of these details to have the better illustration of this cross entropy and then the entropy and so on. Also, as you can see, say if these are the 4 possible outcomes, okay, x1 to x4, and then these are the probabilities, corresponding probabilities of those outcomes. Okay, and then if we compute the entropy, it is what is seen here. Okay, and then the cross entropy is 2. So it's a like the in some sense the information that's there in both of them. Okay, now KL divergence quantifies if we already know the like information content in Q and how much more should we have to reach out to the P. That's what is seen here. You can see that this minus this will give this. Okay, so this is a like an illustration with some example on how exactly the entropy, cross entropy, and then the KL divergence are related and can be computed. And this is another example. So where it clearly illustrates, say what happens, say for example, if this, if you see here, the desired probabilities are different from the predicted probabilities. Now, if we bring these predicted probabilities moving towards these desired probabilities, okay, then what happens? So these values will be closer to this, and hence the information content which is there with in P and Q will be exactly same as what is information content there in P. Okay, that's what is can be seen here. So here moving the predicted probability towards P, okay, gradually taking from the previous example, as you can see, will reduce the KL divergence. Okay, as you can see here, this is 0.25 here, and here it is 0.4. Okay, slightly moving towards 0.5, which is there here, and then here also it is slightly decreased. These two are the probabilities of these two are adjusted such that we are moving from Q to P gradually. When Q equal to P, what we have is the information content in this is exactly there in information content of both of them. Okay, and then the divergence is 0. So these can be used as the possible clues for computing the cost functions in classification problem. In fact, this is the very by default measure for calculating the cost function in most of the classification algorithms. So how, see what in this application, what differs from conventional way of calculating the KL divergence and the cross entropy and KL divergence is that most of the times we have the desired probability binary in nature. Okay, it can be 1 to one of the class, okay, and then 0 to other classes, right? So just to take a simple example, if we have two outcomes, it can be 1, 0 or 0, 1. So in such case, we can simplify the expression of computing the cross entropy and KL divergence. See, before we move on to this, if you observe these KL divergence and cross entropy, assume that P is fixed. Why we are considering P is fixed? Because P is desired probability. Given a particular sample X to any classifier, okay, the probability P we wish to get is fixed. Is it not? So it's a desired probability is fixed in classification scenarios, in most of the classification scenarios. Q is what you get, okay, and P is what we want. Okay, Q bar is what we get and P bar is what we want. Okay, this is fixed. If this is fixed, say, should we consider KL-Divergence as the cost function, or cross-entropy itself is enough to consider as the cost function? What's your comment on that? Do you think actually cost or loss function, okay, should it be KL-Divergence or cross-entropy?
I think cross-entropy is enough.
Yeah, the reason being, loss function being KL-Divergence is exactly equal to loss function being cross-entropy. The reason being what? Why it's enough to have the cross-entropy itself as the cost function? Because
Sir, because cross-entropy itself gives commonness of information, and that's what we are looking for in a loss function. So.
right, and actually h of p is constant, okay, for all samples. Okay, and hence from sample to sample there is no difference. It's just a constant term. Okay, in a cost function, when we consider especially constant terms doesn't change, it doesn't matter. Only what we need is a say finally our cost function has to be a function of say the model parameters and the input samples. This is what is expected. Okay, these are the model parameters. This can be many, okay, millions as well, and these input samples. This h of p is neither a function of model parameters nor a function of input samples. Why unnecessarily hanging there? Okay, that's why cross entropy is widely used or employed as a good loss measure. Okay, so now in that light, if we see, it's enough to see the cross entropy. So in this case now, when especially p bar is 1, 0 and 0, 1, and q bar can be say anything q1, q2. Okay, so how does cross entropy look like? So first, in general, cross entropy, how does it look like? As we mentioned, in general, cross entropy, how do we define? How do you define? Okay, this is how we define. 1, 2, C classes. If we have C classes, I have put C, D, and so on. Okay, please take it based on the context. Okay, hope you understand what the summation is over. Okay, summation is over predicted probabilities. If we consider C classes, okay, then it goes from number of classes. I have put there based on the dimension of P and Q, but in classification scenarios, you can say it's number of classes. Okay, so this is how in general it is defined. Right now, if we know that a priori that it's a binary classification problem, okay, it's just a binary classification problem. That means you have actually an input sample and you have a classifier. The answer is yes or no. Okay, it belongs to class or does not belongs to class 1. Okay, or belongs to class 1, else belongs to class 2. Okay, but actually it belongs to class 1. This is a more apt scenario that we are discussing. Okay, if in some cases, if class 1, if it belongs to it, it already rules out belonging to class 2. Such is the case we are discussing. Okay, if both classes it belongs to certain probability, say 0.82 here, 0.62 here, we are not discussing that. In that case, it goes to general setting. Okay, where you need to use the general expression for cross entropy. Okay, whereas binary cross entropy, what we are saying is the desired probability is equal to 0 or 1, okay, or 1 or 0. In such case, okay, what happens to h of p, HPQ? Can one of you tell? What happens to this? See, in this case, P I can write P1, okay, P2 is
Zero.
equal to 1 minus P2. Sorry, 1 minus P1. I can write like this, right? In fact, since I have only one variable that is required to write the both terms of P1, P2. Okay, I can also write. Okay, so P this is equal to P and 1 minus P. These are the probabilities for defining P bar. P1 minus P. Right? I can define a priori itself. If I know that it's a binary classification problem, the probability is like this. Correct? See, since the P is also P and 1 minus P, okay, decide the estimated probabilities also I would like to have Q and 1 minus P. Okay, because it belongs to one class means it already makes it, okay, not feasible to belong to other class. Okay, disqualifies to belonging to other class. Okay, so in that case now, how do I define the cross entropy now? H. What? We have just expanded this. Okay, Pi is nothing but small p. Okay, and then P1 is nothing but small p. And then P2 is nothing but 1 minus p. Okay, similarly, we have actually Q1 is nothing but Q and Q2 is nothing but 1 minus Q. Okay, given these things, we have just written this. Is it clear to all or not?
Yes.
Yeah, yes. So this is the cross entropy. So now if we have actually, even if we have many dimensions, in that case also, what happens to this cross entropy? When we simplify this, what do you think will happen? Say this cross entropy now, even in this case, if I simplify this, one of the term will become what? If I just start substituting the p equal to 1, 0 or 0, 1, one of the term will become simply 0. So finally what happens? Only one term remains. Okay, so even if I expand this with a kind of binary label, okay, where only one can happen to one class, like all other classes will become 0. Okay, the probabilities become 0. In such case, this expansion will have only single term corresponding to that class probability minus ln of. So if we simplify this, just to give you a multi-class scenario wherein P is equal to 0 and 1 only for a particular class and 0, okay, for a given sample. Okay, so let Xi be the sample. Okay, and then the label, what we have here is yi. So that this is what is particular P of yi, I have written. So that means the label for ith sample is what we are writing. Okay, so this will have actually one for that when it belongs to that class, otherwise it is 0. So in that case, what happens? The cross entropy now, binary cross entropy, or if we write now cross entropy in this case, even in this case, if to this class, if it belongs, all other class 0. Okay, so now cross entropy, if we write, it expands to what? My minus ln of what should come here? Only one term will come. Q of yi. Okay, where yi is equal to, so it can be the class label. It can be if it is xi belongs to class 3, yi equal to 3. Okay, at third index it is 1. Okay, or if xi belongs to class 5, yi equal to 5. Okay, that's how we are defining. So qi is the corresponding label of Q3. That means you can see that yi equal to 3 means this will give me, okay, pi pvi is equal to p3. Okay, this is the understanding of this index. Okay, so what we are doing now, yi means Q3 is what we are picking, and that is directly gives us the cross entropy. Okay,
The cross entropy expression should be minus of P yi into ln of Q yi, right?
right. So let's expand now. Since say what it should be pi, okay, ln of qi. Okay, general expression I equal to 1 to C classes. Okay, so but actually what's there, except for yi if it is a particular class label, except for that remaining all are zeros. So when I expand this, p1 ln of q1 plus p2 ln of q2 plus p3 ln of q3 plus up to 4 classes, I assume that p4 ln of q4. Okay, in this example, for example, C equal to 4 and then yi is equal to 3. Okay, so in this case now, what does it mean? The vector P, if we see, okay, the vector P is what? Explicitly if we write 0, 0, 1, 0. Is this correct or not? For this. Okay, so now if I substitute, what is the answer? Fine. Okay, this is what the example, but in general now, if P of yi is equal to 1, okay, and P of other, okay, so P of j is equal to 0. If j is not equal to yi, okay, then cross entropy is defined as minus ln of q of yi, where xi belongs to class yi. Is this clear? Is this discussion clear?
Yes.
Okay. So hope it's clear for all. Okay. So this is how usual, this simple it is, the cross entropy laws finally. Okay, when we define. Of course, this q of, see if I see q of yi, if I consider any general classifier, see what will happen is x will be input. This classifier in general is parametric. Okay, it will have several parameters, W. Okay, W are parameters of the classifier. Okay, and it gives a label finally. The label it gives is finally Q. Okay, Q or Q bar. Okay, I am writing on the top, but anyway, fine. Q bar. So it will give some probabilities. It's all function of this Q itself is the output, right? Function of W comma X. Okay, so particular Xi, if I consider, this Qi is a function of W comma Xi, right? And then this Qi, we want to use, this is what you have actually. Okay, so from this Qi, capital like Q bar I, where you have several terms, we only pick the term corresponding to the correct class label and then back propagate. Okay, in cross entropy laws. Okay, so it automatically makes other things 0 because we are maximizing that to 1 probability of Qi to 1. And then the Qi function is such that, okay, here how you get Qi is such that, okay, only one of the variable will be 1 in Q and remaining all will be zeros, or the sum of the all elements in Q bar will be equal to 1. That's how this Q will be. Okay, given that, what happens if you are maximizing one of them to 1, or if you are bringing one of them to 1, then it means that all others become 0. That's how naturally the learning happens. Okay, is this clear?
Yes, sir.
No, predict this is what actually gives the predicted probability here. Probabilities. Okay, and then you have actually underlying the true probability. Match with true probability. Okay, and then the last computes. Okay, how much these two are similar. Okay, so and then the what information flow is once how much these two are similar or dissimilar, if we quantify, we would like to learn the parameters W such that these parameters will become more and more aligned or more and more updated such that P and Q agree, the predicted probability and the ground truth probabilities or desired probabilities agree for all samples X, not just for one sample, for all samples X. That's how the parameters are being updated. That's what is the learning. Okay, learning the parameters. Okay, is that clear now? What we essentially do in classification, or in fact, not necessarily in classification. This is done in all the tasks, not only in classification. Let it be in object detection, let it be in sequence models, let it be in tracking, okay, 3D reconstruction, in any task. Essentially, learning happens such that the predicted quantities are moved towards the desired quantities by adjusting these learning parameters W, given all the input samples, not just for one input sample. Is this clear?
Yes, sir.
Yeah, fine. Okay, so now let's see once the other examples, just to see the cross entropy, how is it calculated? You can see that if it is a binary classification problem, the entropy is 0 because you have the information fully in this. Okay, or no uncertainty here. Okay, so and then the cross entropy, if you see, is this, and this is what is the difference to bring this two closer to this. This actually to bring these predicted probabilities closer to the desired probabilities. Okay, as you can see here, these are close to 0.4 and 0.6. That means, and these are 0 and 1. So if you consider a phase detected or not, say this is being say foreground sample, okay, and this is background sample. Okay, when the background sample is given, probability has to be 0. But the algorithm or the classifier, what is it telling? It is roughly giving equal probabilities. What does it mean? It means that the classifier has no information in it yet, and it is simply giving equal priority or equal probability of this input sample belonging to background class or to the phase class. Okay, and hence it has to be learned or trained much more. That's why the cross entropy is high. Okay, and then the corresponding KL-Divergence is also high. Okay, both are proportional as we have seen. In fact, in binary classification problem, you can see that this is 0. So both are exactly same. Okay, there is no entropy here for P, desired samples. So you have actually directly the cross entropy is equal to KL-Divergence. Okay, and then the information to be learned is very high. You have to update reasonably well. Once you train and train, if you move this towards the desired probabilities, then what will happen? This may go to 0.1, this may go to 0.9. Further, if you train, it may become 0 and 1. Okay, then full convergence has happened. Okay, if it is 0 and 1 for not just for one sample, but for all samples. Okay, say if next sample may be a foreground sample. In that case, x1 will be 1 and x2 has to be 0. Okay, so that has to happen. So if like that for all samples, if that happens, then what we say is algorithm is learned. Okay, and the learning is complete. Is this picture clear?
Yes.
Yeah, fine, good. So now what essentially we need to do for any, say, given an image, we say this is an image. Our objective may be to identify where a particular object is, or to classify to one of the classes, or detect an object. Detect an object means in the image where it is. I just want to know, actually this is the correct region. Okay, remaining all are the wrong regions. Okay, for this particular, for a particular template in this case. Okay, so or if I would like to see how much is the, say if I have a sequence of images, image to image, how much is the motion? So for many of the tasks, what are the main things that are required? If we consider, there are two important aspects. What we have discussed is to have a classifier or a algorithm, which will essentially learning algorithm, which is parameterized by parameters W. W can be a matrix, vector, combination of several matrices, combination of matrices and vectors and so on. Okay, it can be of, say, it can be of any dimension. Okay, W means all those put together, R power, whatever dimension. Okay, so I will put R power capital D. Okay, it can be 10 power 6 dimension or 10 power 8 dimension, whatever. Okay, I put everything in W, learning parameters of the algorithm. To tell actually to which class output, say to give the predicted probabilities for our inference problem. And there are some desired probabilities we want to match and then make the cost function. And then minimize and then make the learning happen. That means update W, keep updating W such that these W now will be able to bring Q towards P. That's one aspect. One aspect is learning. There is other aspect that's very important. What is the other aspect? Can anybody tell what is the other aspect that's very important given for image processing problems? Say here is a face image or a person image or a face. What we want to see? We don't want to take direct pixels into account. Is it not? For all this learning task, you should have very effective features. Either it be one dimension or it be two dimensions. Okay, so we need to have a feature representation. So how do I find features of the, say, let it be one dimension or two dimension? How do I get the raw signal or raw data information, signal or data? Two features to have an effective learning happening. Okay, so feature representation or feature extraction also plays an important role, especially in an image where I want to look is also plays an important role. So in the next class, we will discuss some of the aspects of feature extraction. Okay, and then after a while, we will come back and discuss the about of learning. Okay, and then we will discuss the whole things in a single framework as well as we discussed.